Hello everyone, my name is Yuke Wang, a fourth-year PhD candidate in UC at Santa Barbara. Today, I would like to introduce our work QGTC, Accelerating Quantized Graph Neural Networks via GPU Tensor Core. Nowadays, graphs are everywhere in our daily life, and graph neural networks are usable hammer to get insights from those graphs. We can find their application in social networks for friend recommendation, financial service for fraud detection, molecular classification in chemistry and biology. Next, we will see how GNN operates under the hood. Let's start with some basic background of the GNNs. In the first diagram, we show the basic computation flow of GNN. Like DNN, GNN also organized by layers stacked together, but the operation is changed from those dense linear algebra, like the convolution, to sparse linear algebra, like scatter-gather. Each GNN layer consists of an aggregation and update operation, where the former follows the graph-like operation, and while the latter updates the node itself by using the information from its neighbors. We also have several observations of the GNNs that indicate its potential for quantized execution. The first one is that the adjacent matrix of GNN is naturally well suited for quantization. Therefore, using 1 or 0 to indicate the existence of edge connection is enough for maintaining the original information of graph structure. And the second point is that the quantization of the weight and node embedding can also be beneficial. The precision loss in quantization can largely be offset through the iterative neighbor aggregation. Meanwhile, this will increase the robustness of the GNNs when encountering adversarial attack and input perturbation. On the other side, the recent hardware advancement of the GPU and programming toolset enable us to leverage the powerful tensor cores on recent GPUs for deep learning acceleration, as illustrated in the right side figure that indicate the layout of the tensor core in the modern GPU stream multiprocessor subcore. And it basically supports the dense matrix multiplication on the GPU. And for programming of the tensor cores, we can use the cuBLAS library, and we can also call the web matrix multiplication accumulative primitives in CUDA-C. However, directly connecting the quantized graph neural networks with the existing GPU tensor cores are facing several challenges. The first one is that the current tensor core can only support the limited choice of the bit width. Therefore, it is unable to meet the demands of users of any bit width precision demands. And second, tensor core initially tailored for dense GEM computation, which may not be directly fit the context of the sparse GNN computation. It will lead to a huge waste of computation and memory access on those long-existed edges. And finally, the low bit computation would cause the compatibility issue, because it will be unable to integrate with the existing systems that operates on the predefined data type, such as FP32 or Int32. To bridge this gap, we introduced our design, QGTC, which encompasses several components. At the first part, we do our work on the input level. We leverage the methods for generating the dense small subgraphs for sparse large graphs. At the algorithm level, we use the 1-bit based quantized computation for arbitrary bit width QGNN computation. And further, at the GPU kernel level, we leverage the 1-bit adjacent matrix, 3D stack bit compression, zero-tile skipping, and the non-zero tile reuse. And finally, we integrate our design with the PyTorch framework. In these slides, we will introduce more details of our 1-bit based quantized computation. Let's start with the basic scatter-gather multiplication with a 3-bit number A and a 2-bit number B. We first decompose the value of A and B into a set of factors in 1-bit representation. When we multiply A and B, we will conduct the cross products on those decomposed factors and do the accumulation. On the right-hand side, we will generalize such 1-bit based scatter-gather multiplication to a 1-bit based vector-vector multiplication, where we can see we will still follow the same process of the scatter-scatter multiplication on each element of the vector, and finally do the cross-element accumulation to get the final results. Based on our 1-bit based vector-vector multiplication design, we will introduce our 1-bit based quantized matrix multiplication with the following steps. The first step is the input number bit decomposition. The second step is the neighbor embedding aggregation. And the final step is the node embedding updates. For memory efficient data storage, we introduced a 3D stacked bit compression to efficiently pack the bit data into an int32 data. The figure shows a case with a 3-bit input embedding matrix, which are decomposed into a 3 1-bit input bit matrix. Element of each 1-bit matrix is packed either along the row major or the column major dimension, depending on whether it's a left or right operand. Another kernel-level design is our zero-tile jumping technique, where we can explore the existence of non-zero elements inside a matrix tile to determine whether we need to carry out a matrix multiplication on those tiles. We also incorporate a non-zero tile reuse design, which we will prioritize the final output result generation of a small output tiles by reusing those already loaded 1-bit adjacent matrix tile. And for PyTorch integration, we introduced our bit tensor data type. We use the 32-bit integer tensor in PyTorch as the vehicle for holding any bit with quantized numbers. We also introduced API for encoding and decoding from and to those arbitrary bit data type. And we also carry out our computation directly on those low bit data type by using our customized APIs. In our evaluation, we evaluate several models, including the cluster GCN model, batched GNN model, and we compare several baselines, including the deep graph library, cuBLAS, and Cutlass. And we have our platform configuration on a desktop server with the NVIDIA Ampere 3090 GPU. And here the dataset coverage across different kind of domains and the different kind of dataset size or scales. In terms of end-to-end performance, we compare with the DGL on cluster GCN. We get a 2.6 times speed up and 2.8 times speed up compared with the DGL on batched GIN. And we also compare our kernel level performance in terms of throughput with respect to the cuBLAS gene int8 position. And as we can see from the right-hand side figure on the rightmost, and we can see the performance is evidence in terms of the throughput. We also carry on additional studies, including the comparison at the kernel level throughput with the Cutlass int4, which is an even lower bit compared to the lowest bit that can be supported by the cuBLAS kernel. And we can also demonstrate the evident throughput advantages over the Cutlass int4 because our design can really harvest the bit level performance compared with the Cutlass. And finally, we evaluate our non-zero time jumping efficiency in terms of the percentage that we can save. And our design can achieve the 70% reduction of skipping those non-zero tile. And this study also covers the adjacent matrix style impact on our performance. As we can see from this figure, our design can scale well with the increased size of the inputs and to approach the upper bound of the GPU tensor core. And our non-zero tile reuse can improve the throughput performance on those large matrix size with a higher number of bits because of saving the unnecessary data loading. And thank you, that's all my talk.